Thank you very much. And I'd like to start by thanking the organizers very much for the opportunity to give this series of talks here at the conference. It's a great pleasure and a great honor for me to do this. The title of this lecture series is Intrinsic Diophantine Approximation, and I will, of course, not define it now. This should become, I hope, hopefully a lot clearer as time goes by. I will just say, though, one word about it, that a lot of the motivation of intrinsic Diophantine approximation is to extend or generalize aspects of classical Euclidean Diophantine approximation to the non-Euclidean setting. Before I start, I would like to say that all of the results that I'm going to be discussing here are based on joint work with Alex Gorodnik and on joint work with Anish Ghosh and Alex Gorodnik. And before we start, I would like to say that I hope intrinsic Diophantine approximation is an emerging topic, which is fairly recent, and I would like to start by a leisurely exposition of some of the motivation and some of the connection that it has to other topics, and I'm going to try to emphasize, at least in the first talk, a certain geometric point of view, and this is partly because I'm very happy to see that there are a lot of graduate students here, and hopefully this will be easily accessible, and I apologize to the expert. It's going to take a little bit of time before we get into more advanced topic. One last thing I would like to say is that please feel free to stop me at any time and ask questions. If there's anything which is unclear or comments, they're all welcome. And finally, in this first talk, I decided not to elaborate very much on the references. I still have 2 more talks, so detailed references and background and relevant results will be discussed in greater detail later on, and not in this exposition. Okay, so let's start. The plan of the first talk is that we're going to begin by talking about density of uniformly discrete point sets, who already made an appearance in Jen's talk, of course. And then we're going to talk about the discrepancy of dense point sets. And then we're going to talk about equidistribution theorems in homogeneous isometric actions. This is our plan for today, and this will all be phrased, as I said, as a geometric motivation. So, so let G be a locally compact second countable unimodular non-compact group with Haar measure, Mg. And to be definite, let's fix a left invariant proper metric D on G and denote the metric balls by dtx, the set of y. Yeah, well, okay, I'm sorry, this is my first typo. G here should be L. Okay. And we denote the ball centered at the identity by dt. And let P in G be a uniformly discrete configuration, namely a countable set of points whose mutual distances have a positive lower bound. Then P, of course, deposits only a finite number of points in any compact subset of G, namely it is locally finite. And one basic question is, does the configuration P have a limiting density with respect to the metric? Namely, as T goes to infinity, is it the case that P deposits in dtx a number of points which is proportional to the measure mg dt? This is certainly a very natural notion of density. And so in other words, we're asking whether the limit of the size of the intersection P of P with dtx divided by the measure of dt converges to some positive limit to rho. This is a really basic question you can ask about such a configuration. And of course, for G equals RD or G equals ZD, these configurations are known as quasi-crystals, and they have been extensively studied for a very long time. And we saw proof of that in the last hour in Jens's talk, where some configurations of this type have been presented. And there are many questions related to them. And this is part of what we will be trying to do. We will try to consider also for a non-commutative group, where the configurations have been termed non-commutative quasi-crystals. They are, in some sense, equally natural, but their study has attracted considerable attention in recent years. But it's not really remotely as advanced as the Euclidean case. Okay, so one thing I would like to say now is that when the passage from commutative to non-commutative configurations, or configurations in non-commutative groups, is really a big step, and a lot of strange things can happen. To be completely honest, when I say non-commutative, this is really not what I mean. What I really mean is non-amenable. That's going to be the source of most of our examples, and there all sorts of strange things might happen. So for a uniformly discrete configuration, even a relatively dense one, namely one that meets every ball of some fixed radius, it may in principle happen that the limiting density that we're after does not exist at all for this point set. That can also happen in the Euclidean case, of course. It could happen that the limiting density exists for a family of balls dt with arbitrary center, but its value will depend on the center. And the limiting density may exist with respect to some metrics, some very natural, some metrics, but not others, which you may consider equally natural. But for a particularly nice class of configurations, this problem does in fact admit a general solutions. And these configurations are truly nice, and they have already appeared in Jens's talk in the Euclidean case. So these are the cut and project quasi-crystals. So let L equals G times H be the product of two locally compact second countable unimodular non-compact groups. And let W in H be a compact set of positive Haar measure, which some people call a window, but you actually called it, you had a different name. A slab, okay. A slab. Well, either a slab or a window.
The slab is this thing, and the window is this person.
Ah, okay. Yes, of course, yes. Yes. So we take a compact subset of H, and we do not want to allow, I mean, general sets can be really crazy. We want W to be regular in the sense that we will make explicit. And then we consider gamma in L to be a discrete lattice subgroup. And we assume that the projections of gamma to G and H are both dense and both injective. This is all not strictly necessary, but it's going to make the statement simpler. So gamma will then be called an irreducible lattice in L. Yeah, that's a good point. I don't insist on it, no. So in other words, that means that gamma, okay, it's a member of, it's an element in this product, so it consists of two components, the G component and the H component, which can also be denoted by pi G gamma pi H G, where these pi G and pi H are the two projections. No, if it's not UG modular, there's no lattice. So it's completely beside the discussion. Okay, so the cut and project quasi-crystals associated with this quadruple G, H, gamma, and W is the uniformly discrete configuration P consisting of all the G components of elements gamma in gamma whose H component is in this compact window. Okay, and so okay, so this is the projection, I guess, to G of the slab. Okay. Now, we've already seen some examples of cut and project quasi-crystal. Maybe, okay, so the first example is where L is Euclidean space, which is decomposed as a product. And gamma is an irreducible Euclidean lattice, namely one so that both of its projections are dense to the component. One, maybe the most simple example of this is when L is the plane, D is a positive non-square, and we consider the ring Z square root of D with the standard involution, and we consider the irreducible lattice, which is, well, spanned by 1, 1 and square root of D minus square root of D. This is the easiest example to write down. A much nicer, much more interesting example, which I was very glad to see a little bit earlier, was in Jens Markloff's talks, for example, the set of vertices of the Penrose tiles. And so these cut and project Euclidean quasi-crystals are really very, very beautiful and profound objects, including all the nice quasi-crystals that one encounters in the literature about Penrose tiles and other constructions of this type. So it is certainly very natural to try to develop a theory which is non-Euclidean, and as easy as it is to write this, this system, one can take for the group L SL2R times SL2R, certainly a very nice familiar group, and one can take the countable subgroup gamma D, which is gamma and then the Galois involution sigma applied to gamma. It's an element of the product, certainly, and here gamma is going to range over the 2x2 matrices with determinant 1 whose entries are in the ring Z square root of D. And it's a fact that, gamma D is in fact an irreducible lattice in L. The fact that gamma D is dense in SL2, that's a little exercise. The fact that it's discrete in SL2R times SL2R is also not very difficult, but to show that it's a lattice requires a certain amount of work. Of course, this is part of a very big theory, of course, it's a consequence of a very well-known result of Borel and Harishchandra from 1960, but I don't really think you need that theorem in order to prove this directly. Okay, so we have the same ring of integers, Z square root of D. We have these classical Euclidean, irreducible Euclidean lattices that are subject to extensive theory. And basically, and this is part of what we're trying to propose, we can try to develop a theory for non-commutative or, well, point configurations or cut and project quasi-crystals in this setup. Now, another important example is that we can consider P in N to be any prime and consider the ring Z1 over P the ring of rational numbers of the form A over P to the K with A and P relatively prime, namely those whose denominator is a power of P. Okay, that's a nice subring of Q. And this subring of Q, Z1 over P, is contained, of course, in QP, where QP is the field of p-adic numbers. And the diagonal embedding of this ring in the product R times QP, simply taking Z to the pair, ZZ, represents the ring Z1 over P as an irreducible lattice in this product. And so, by using the same idea, we can then once again consider another group, SL2R times SL2QP. And we can consider the diagonally embedded subgroup, lambda P is R, comma R, where R is an SL2 Z1 over P, namely the 2x2 matrices whose entries are in the ring Z1 over P. So these are rational matrices, 2x2 rational matrices, all of whose entries are of this form. And this, again, is an irreducible lattice of L. And once again, this is not a fact that everybody will recognize immediately. In general, as I said, gamma D and lambda P are examples of irreducible S-arithmetic lattices in linear algebraic groups, an extensive class which appears in many applications, and specifically, it was shown that in much greater, for all of this class, by the Borel-Harish-Chandra theorem, that in fact we do have a lattice, an irreducible lattice. Okay, so so far this is part of the gist of what we're trying to do. We are trying to consider a number of aspects of classical Euclidean, in this case, point set configurations and move it beyond the Euclidean setup. Okay, so we would like to consider the existence of density for cut and project quasi-crystals. And so when L is Euclidean and we have an irreducible Euclidean lattice, and D is, let's say, the Euclidean norm, the existence of the density follow from a much more general result of Schlottmann, and in fact, normalizing the covolume of the irreducible lattice to be 1, the density, this should be rho, our density previously was rho, the density rho is the volume of the window. And this gives us, of course, an idea of what to expect. And so we have the following proposition. A cut and project quasi-crystal P in SL2R associated with one of the irreducible lattices gamma D or lambda P, and associated with one of these lattices any regular window and any metric on SL2, given, for example, by a norm or an invariant Riemannian metric, does indeed have a density. The density, as we defined, it's going to be measured using dt for any dtg for any point g in G. Okay, maybe this is formulated in a way which is a little opaque. The gist of it is, okay, you take your irreducible lattice, you project it, you take the window or the slab more precisely, you project it to the component SL2R, and then you look at this growing family of sets, dtg, and you ask how many points are you going to see from this configuration in a large ball, And if you normalize by the measure of the ball, are you going to actually converge to a limit? And this limit is what we call the density. And the answer is yes. You can take any regular window. The regularity will be explained in a minute. You can take any of these lattices, and you can take a wide choice of dt, for example, associated with a linear norm, or invariant Riemannian metric, and you will get a density. And as we by now expect, if we normalize Haar measure so that the lattice has covolume 1 in L, then the density is given by the measure, the Haar measure under the second component of the window, now W. Yes. That's 100%. This problem is going to have a very simple solution, like you say, and this is the reason I wanted to start with this. It's going to admit a very simple solution, as you point out. Yes. You will see in a minute, according to the structure of this proof. Okay, so establishing density for cut and project quasi-crystal is an instance of a much more general problem. And that problem is the lattice point counting problem for irreducible lattices, or for lattices in general. Okay, and so indeed, in our setup, as Dima pointed out, essentially, the point set P, namely the set of G projections of the points gamma and gamma whose H projections are in the window, this is the point set P, and so the points in P intersect dt, whose number we would like to count, are precisely the projections to G of the set of points in gamma intersect this set. The product set, dt times the window. This set is a nice, well, I don't know, a nice compact set in the product group. A nice compact set of positive measure in the compact group. And so the numbers that we actually want to count are given by the intersection of the irreducible lattice gamma in a nice, with a compact set in a nice locally compact group. And so this is an instance, therefore, of the lattice point counting problem. You have a family of sets which have positive measure, which grows, and then you want to count the number of lattice points in them. And so proposition A therefore follows from a positive solution to the lattice point counting problem for general families of sets, BT, any BT, it doesn't have to be a product set, contained in this locally compact group. And of course, BT includes the families DT times W, so the lattice point counting problem wants to show, the solution of it wants to show that the intersection of gamma with translates of these sets, BT, divided by the volume of such a translate converge to 1. The number of lattice points is asymptotic to the Haar measure. So that is what we call a solution, a solution to the lattice point counting problem in this family of sets. Of course, the one, the one has to do with the fact that here we implicitly normalized the lattice gamma to have covolume 1. Okay, so the lattice point counting problem admits a general solution. Yes. Sorry? Yes, we are now going to discuss precisely what they have to satisfy. Yes, exactly. Now, so the lattice point counting problem admits a very general solution, and I would like to discuss what is necessary, or well, I would like to discuss what kind of conditions we should impose on BT so that we will be able to get a positive solution. And there's going to be two ingredients to this. Sorry. One is a regularity condition on the sets BT. This condition, a regularity condition, is absolutely necessary. Notice that the lattice point counting problem wants to identify points from a certain countable set. The whole group gamma is countable, and we want to find specific points from a countable set inside other sets. Now, if you're going to take any set whatsoever and you're going to throw out this countable set from it, then you're going to get the same Haar measure. And so the lattice point counting problem, the lattice point count in that case will be 0. So it's absolutely clear you cannot give any positive result for sets which do not satisfy regularity conditions. This is, in this case, this part is completely obvious. Now, the second ingredient is going to be a mean ergodic theorem for the averaging operators supported on BT. And these mean ergodic theorems are going to be an absolutely crucial part of everything we're going to talk about in this talk and the two next ones. And so it'll be a good thing to introduce it early. And that's what we're going to do now. So as to the regularity conditions, these are called well-roundedness. And they're defined as follows. It's actually a very natural condition. So for a family of sets BT in L, any L, we consider the following properties. BT are called well-rounded if for every positive delta there exists a positive epsilon and some T delta such that for all T greater than T delta, if you take your sets BT and you perturb it on both sides by a small neighborhood of the identity, this will obviously increase the set BT, and so this set is going to have greater Haar measure. And the regularity condition is that the increase in Haar measure is well, it's bounded by 1 plus delta times the Haar measure of a set which is smaller than BT, namely the intersection of all the translates of BT by U and V, where U and V are in O epsilon. So you should, the easiest way to think about it is you may want to think about BT as a round ball, and then this will essentially amount to increasing the radius by epsilon. I mean, this is what happens in metric cases, and this would essentially amount to decreasing the radius by epsilon, and so you're basically saying that the volume of the larger ball is dominated by 1 plus delta, the volume of the smaller ball. And here, O epsilon is a family of compact symmetric decreasing neighborhoods of the identity, whose measure, of course, converges to 0. So this is a very nice sort of geometric regularity condition, which is very popular, and it appears in many, many lattice point counting problems in the literature. It was introduced a long time ago. And to be a little bit more precise and quantitative, which we will have a great interest in doing, BT are called Lipschitz well-rounded if there exists a positive C and a positive epsilon naught and positive t naught, such that for all epsilon between 0 and epsilon naught and t greater than t naught, the bound on the ball of larger radius, shall we call it, or this perturbed set, is bounded by 1 plus c epsilon times the volume of the smaller ball, shall we say. And here we will assume also that O epsilon is a shrinking system of neighborhoods such that its Haar measure dominates epsilon to the d. So, of course, whenever you're going to have a group with a certain, a connected group with a certain dimension, then, of course, you will simply take small metric neighborhoods of the identity, and their Haar measure is going to be given by, it's going to be comparable to the Euclidean measure, so it's going to be epsilon to some power d. Okay, d, of course, being the dimension. Okay, so these conditions are very, very well known and well established, and let's now move to the definition of mean ergodic theorems. So this is going to be the beginning of our spectral approach. We will describe the spectral approach to counting lattice points. So for each BT, we can define an averaging operator, beta T, which is going to act from L2 of L mod gamma to L2 of L mod gamma. Now, this space, L2 L mod gamma, it has a unitary action by the group L. The group L acts by translation on any homogeneous space, and in particular, it acts by translation on the homogeneous space L mod gamma. L mod gamma has an invariant measure, in fact, an invariant probability measure, and so we have a unitary action of L in L2 L mod gamma. And so from that, we define the following averaging operators. Beta TF at the point x gamma. Well, we're going to look at F at the point y inverse x gamma, so we are translating by elements y in BT. And then we take the integral with respect to y in BT, with respect to Haar measure on y. And then we normalize everything by the volume of BT. This is the absolute obvious generalization of the standard ergodic average, as it sometimes called. If you were to take R as your group L, and if you were to take BT to be your interval from 0 to t or from minus t to t, and you would form the standard ergodic averages or von Neumann averages or however you want to call them, then this is precisely what you're writing. It's the integral, let's say 1 over t, the integral from 0 to t of f, well, y, x gamma d, dmly. That's precisely the same expression. So this is the most obvious generalization of the ergodic averages. And we will say that the family BT satisfies the mean ergodic theorem in L2 L mod gamma if these averages, beta TF, minus the space average, as it is called, the integral over L mod gamma of F, converges to 0 in L2 norm. And so everybody here is very familiar with the mean ergodic theorem. This would be the classical mean ergodic theorem for R actions. This would be the generalization. But now I would like to introduce, and again, this is in the spirit of moving from the Euclidean situation to the non-Euclidean situation, I would like to introduce a far, far, far stronger mean ergodic theorem. And this mean ergodic theorem is a non-Euclidean feature. And this is the following. It's the the family BT satisfies the effective mean ergodic theorem in L2L mod gamma if there exists positive theta such that for all f in L2 gamma, the L2 norm of the difference between the time average and the space average actually decays to 0 as a certain negative power of the volume of BT. So this is far, far, far more precise than this, and it gives you a rate in which the ergodic averages converge to 0. Yes? Okay, so since you asked, so the general definition of a mean ergodic theorem will put here a general space, any probability space on which the group L acts. The non-Euclidean feature is that, for example, for the group SL2R, which we are occupied with, for the group SL2R, you have probability measure preserving actions, for which this volume estimate actually holds for all functions f, and if you look, for example, at the classical ergodic theorem for R actions, this cannot be the case in any action of R which is properly ergodic. You cannot have any rate of convergence for all functions in an ergodic measure preserving properly ergodic measure preserving actions of R. This can only happen if the group is non-amenable. So yeah, I'm using non-commutative, non-Euclidean, and non-amenable as interchangeable appellations, but of course they're not. This can only happen in the non-amenable case. Yes. Yes. Mixing is far, far weaker than this. This is much sharper than mixing. Much, yeah. Although, of course, I mean, I should say that both mixing and this fact, they derive from the same fact, which is estimates in the unitary representation of L on L2 G mod gamma. But mixing is a much weaker conclusion of this spectral theory of unitary representation. Okay, so now we can finally state the following. So we have a solution of the lattice point counting problem. So if L is a locally compact, non-compact, again, unimodular group, gamma is a discrete lattice subgroup, and M is the invariant probability measure on L mod gamma. Then if BT is well-rounded and satisfies the stable mean ergodic theorem for beta T, then we have a positive solution to the lattice point counting problem. Stable? I'll say that in a minute. Well, okay, I'll say it now. Stable means that you have the mean ergodic theorem not only for BT, but also for BT and its in the small perturbation. But it's really, okay. Let BT be Lipschitz well-rounded and satisfy the effective stable mean ergodic theorem in L2 L mod gamma. Then we have an effective estimate in the lattice point counting problem, namely the number of lattice points in BT, it's 1, and the error estimate is, it decays like a negative power of the volume. And here we have the difference that rather we have compromised the error. We don't have error which is minus theta, but minus theta divided by d plus 1. Okay, so let me make a few very quick comments. The stable mean ergodic theorem requires the validity of the mean ergodic theorem not only for the family Bt, but also for its O epsilon perturbation. The reason it's there is because this theorem is really formulated very generally for all locally compact groups. But actually, in practice, this is not really an additional condition, and specifically for the lattices in algebraic groups, this doesn't come at all. It's completely irrelevant. So specifically for the lattices gamma d and lambda p, the mean ergodic theorem for Bt is sufficient. And anticipating what we would like to do a little bit later on in this lecture series, the scope of theorem A is quite extensive. It includes lattices in connected simple Lie group, irreducible arithmetic lattices in S algebraic semisimple group, and even the lattice of rational points in semisimple Adel groups. But actually, it also applies to other classes of algebraic groups. Things do not have to be simple or semisimple. You can consider affine groups and other groups with a unipotent radical because the formulation of that theorem is really quite general. And now Lipschitz well-roundedness for the family dt usually requires a careful study of the volume growth in G. Volume growth in general is a very tricky matter in these complicated groups like SL2R and its variants. And theorem A applies in particular to the sets Bt equals dt times W, which are associated with cut and project quasi-crystals when they are well-rounded, or Lipschitz well-rounded. So when dt has these relevant properties, this depends only on the regularity of the window. So the bottom line is, if you take a regular window, then the cut and project quasi-crystal does in fact have a density in the cases, in the examples that we had before. And now the validity of the stable mean ergodic theorem for a given family Bt must be established using spectral analysis in the unitary representation of L in L2L mod gamma, which is called the automorphic representation. This is a key element for us, and we will consider it in much greater detail later on, but I thought I would introduce it as early as possible. So you can ask me, why should you believe that the sets dt times W actually satisfies the effective mean ergodic theorem? An excellent question, and certainly something that came into the solution here, but let me not do this right now, and we will get back to the automorphic representation later. But the fact that the configuration has density, it rests on regularity, and regularity is in your hands. You can take regular dt and regular W, and on the mean ergodic, effective mean ergodic theorem, which you have to prove using spectral theory. And theorem A generalizes non-Euclidean lattice point counting results due to Duke, Rudnick, and Sarnak, and Eskin-McMullen. These are very well-known results from 1990. Gorodnik, Mokorant O, Benoit O, and some others. And one thing, again, anticipating what we're going to do later on, I would like to say is that the spectral method that is employed in theorem A is an efficient one. For example, for higher rank simple algebraic groups, the effective error estimate it provides matches or improves all the previously established error estimate. These error estimates are going to be crucial in effective and quantitative results that we would like to establish in Diophantine approximation. And that's why I'm mentioning them here. And yes, we will use the effective error estimate in the lattice point counting problem in a number of applications. Okay, let's talk now in the 10 minutes that are left about density and approximation. And again, consider the example of L equals SL2R times SL2QP and the lattice that lambda P that we had before. And now consider the set of rational matrices in SL2ZP with entries of bounded denominators. the set of R in SL2 Z1 over P, the denominator of whose entries is bounded by P to the H. And now let's take as our windows the set WH in SL2QP, which is the closure of BH in SL2QP. WH is a compact and open subset. It's a very nice subset, and there's no problem using it as a window. But notice that now I'm going to take the windows to be very large. I have a whole family of windows. And so the slabs are going to become bigger and bigger, and because of that, the projections are going to become denser and denser. Is this geometric picture clear to everybody? Okay, so now, as age increases, the corresponding cut and project quasi-crystals associated with WH becomes more and more dense in SL2R. And in what follows, we propose to quantify the rates of increase of several significant aspects of this density. This will bring us right into the topic of intrinsic Diophantine approximation. And so our first goal is to estimate the speed of approximation of a real matrix in SL2R by rational matrices with entries in Z1 over P whose denominators are bounded by PH. In other words, this is the same thing as saying it's one aspect of the question of how dense do these projections become? Or how fast do they become dense? Or I don't know exactly how to formulate it. So we seek to solve the inequalities. The norm of x minus r is less than epsilon, and the denominator is bounded by 1 over epsilon to the zeta. With R in SL2, a rational matrix in SL2 Z1 over P, we want to solve this for all epsilon sufficiently small, and with a speed of approximation zeta being finite, positive, and independent of x. And so we let kappa be the infimum of zeta, of positive zeta, which satisfies these properties, and call it the exponent of uniform approximation. It certainly is not obvious from the definition that it is finite. Okay, but we certainly have some exponent that we have defined. And similarly, we can consider the lattices gamma d in SL2R cross SL2R, and the windows being given by norm balls. That's another family of increasing windows, which will produce denser and denser projections, denser and denser configurations. And we seek to solve the inequalities, the norm of x minus gamma less than or equal to epsilon, such that the norm of gamma sigma is bounded by 1 over epsilon to the zeta. And here, so here gamma d, gamma is in the lattice gamma d, which is SL2 z square root of d, and sigma is the Galois involution. Okay, and so let me state the result, which was proved with Ghosh and Gorodnik some time ago. So this is going to be a consequence of, these propositions are going to be consequences of more general results. So for these dense subgroups, lambda p and gamma d of G equals SL2R, there exists an explicit estimate of the exponent of uniform approximation kappa in each case. And so you can say that you can put a certain number here, and you will here, and you will get in this case, your rational approximation to x with a rational matrix, and you will pay only a certain price in the size of the denominators. It's going to be 1 over epsilon to some fixed power kappa. Yes? Oh, I wanted to be explicit very, very much, but not in this talk. We are going to discuss exponents a lot, but not right now. It's just going to be too many things to introduce. It's an interesting question. I've never seen a result that actually says that you have a finite exponent of uniform approximation, say in this case. So I'm not sure. Maybe there is an easy argument without saying anything about the size. I mean, something would have to be used. You can take an arbitrary dense subgroup of SL2R. And, okay, so there are a lot of those. And so is it completely obvious? I don't know. Okay, so, and so now, we still have, do we still have, well, we still have 3 or 4 minutes. So let us now talk about equidistribution of dense point sets. And so, and put it in a somewhat more general perspective. So let X be a locally compact, but not necessarily compact metric space. Yeah, I forgot actually, the last statement I wanted to make is that this estimate is quite close to being optimal, and we will come back to this point. We will describe it. And so we have a locally compact metric space, and we have a radon measure on X positive on open sets. And we let RH be a collection of locally finite subsets of X, namely the intersection of each RH with any compact subset of X is finite. And we will assume that the union over H of RH is a countable dense subset of X. So we already know an example of this. We've been discussing this all along. It's the union of these BH, for example. And the collection of sets RH is said to be equidistributed in X with respect to nu and some rate function VH. If there exists a function VH converging to infinity such that for every bounded domain omega in X with boundary of measure 0, the number of points RH that fall into our domain omega normalized by VH, converges to the this radon measure of omega. And so this is going to be our definition of equidistribution. I want to emphasize that we are talking about actually a very complicated situation where X is not compact. For example, X could be SL2R, and there is no a priori obvious normalization of these intersection numbers. And we are discussing equidistribution in a non-compact situation. Okay, or an infinite measure situation, it's better to say. And so, given this equidistribution as we defined it here, one can ask about the discrepancy of our sets RH. And we define the discrepancy as the number of points RH in omega divided by this normalization minus nu omega. So it's how close we are to the limit. And the discrepancy obviously measures the deviations of the sets RH from being fairly deposited in the set omega. Fair, of course, is being close to nu. That's what fair means. Now, taking omega to be bx delta, small metric balls, the condition that the limit as h goes to infinity of the discrepancy of RH with respect to this small metric ball is 0, means that the pointwise discrepancy of the family of sets RH at scale delta at the point x vanishes asymptotically. This problem comes inherently with a scale. And the scale is very important. Now, a bound of the form d, the discrepancy is bounded by this normalization to the power minus tau for some positive tau, as x varies in a compact subset of x, gives an effective rate of the vanishing of the locally uniform pointwise discrepancy of the family RH at scale delta. So the point of what I've been trying to say is that we are looking at
finer and finer, or more and more precise gauges of density. And here we are talking about a very fine gauge where we look at our locally finite set, and we actually measure how many points it deposits, let's say, at scale delta, and we are able to normalize it and get a density in the limit. So this is a very fine gauge of density. And our second goal is to establish an effective bound for the uniform discrepancy of Z1 over P points in SL2 at arbitrarily small scale. And I'm just going to put one or two more slides and just to say what the result is. So we consider, again, the previous elements BH. I hope everybody realizes this conforms to the assumptions on RH. For any bounded domain and any fixed H, the intersection of BH with omega is a finite set, and the union is dense in omega. And we let WH be the closure in SL2QP of BH. And now our choice for the normalization VH is the Haar measure of these compact sets WH. That's our normalization. And the discrepancy is therefore given by BH intersect omega, the number of points divided by VH minus Haar measure. And the equidistribution result underlying the definition of discrepancy is, in this case, a consequence of the well-known equidistribution result for Hecke points together with a duality argument. And we're going to be back at this point, but let me just finish with this proposition. For every fixed scale delta, the following effective uniform discrepancy bound holds. The number of points that BH deposited in a ball near the real matrix G of size delta divided by this normalization is bounded by VH to the minus tau. With tau, again, it's going to be explicit and independent of G. And another important point we will discuss later is a joint estimate in both age and the scale delta. Okay, so thank you very much for your patience.